We didn't do this problem last time, but we were talking about when you have competing acids. So if you have a strong acid and a weak acid, or if you have two weak acids, or if you have, actually I don't think we did for weak acids that had similar Kas. So you got to think about here on this problem, which of these are strong acids, which are weak acids, and which one's going to be the most acidic or have the lowest pH. Yeah. A is going to be the most acidic because it's got a strong acid, so it's going to dissociate completely. All the other ones are weak acids, so we'll only get partial dissociation. Do I have, I don't think I have those. Yeah, I do. So this is 2.9 times 10 to the negative 8. And 6.9 times 10 to the negative 4. Those are their Kas. Which is the stronger acid? The larger Ka. Which one has the larger Ka? Hydrofluoric acid. And honestly, on this kind of thing, if you want to just write it out as, like, convert it into decimal notation, here's 6, 9, and then this one is 0.2, 3, 4, 5, 6, 7, 8. Makes it a little bit more apparent that 10 to the negative 4 is the larger Ka. So that's the stronger acid of those two. And now bases. So there are a lot of strong bases, but they all look the same. So it's not like you have to really memorize all that much more. They're all going to be a metal plus hydroxides. And unlike polyprotic acids, so I've already mentioned a couple times that things like H2SO4, strong acid for the first proton, weak acid for the next proton, they come off in succession. So if I have like 0.1 molar H2SO4, it's not like both of those hydrogens come off. The concentration of H3O plus will be about 0.1 molar H3O plus. For strong bases that have two hydroxides, so the strontium hydroxide, the calcium hydroxide, and the barium hydroxide, those hydroxides both leave at the same time. When they dissociate, you'll get, actually I think this is the next, no. So like if I had a 0.1 molar calcium hydroxide, the H3O plus concentration is going to be 0.2. Or not H3O plus, wow, OH minus. Because I'm getting two hydroxide ions. It's pretty much the group 1A, group 2A hydroxides, alkali metals, and the alkali earth metals, they dissociate completely. Weak bases most of the time do not have hydroxides or form hydroxides directly. They have, they take a hydrogen from something else. Ammonia is one common weak base that you should already know. You've used it a lot in net ionic equations. But basically anything with nitrogen in it will also be a weak base. or I guess organic molecules with nitrogen in it. So if you get something like a CH3NH2, that's methylamine, that's going to be a weak base. If I add more another CH group, that's ethylamine, also going to act like a weak base by taking hydrogens from water. And everything is equilibrium. So of course we have a equilibrium constant, or also known as the base ionization constant, Kb. So same thing as Ka, but for bases. The big difference is in how the equation, actually, the equation gets written out basically the same. I have my base, it reacts with water. But instead of donating a proton to it, it takes a proton from it and gives me my base now with a hydrogen and a positive charge, and then the hydroxide. And a smaller Kb means a weaker base. We can also calculate pKb the same way that we calculate pKa, or pH, or pOH. It's just negative log. Here's some more weak bases. Most of them, oh, I just broke in my pocket. Most of them, notice, are methylamine, ethylamine, ammonia, even pyridine has nitrogen in it. So it's like carbons, hydrogens, and then a nitrogen in there. That's going to be, even aniline is a weak base. Other ones that are notable that'll come up in actually just a little bit are things like carbonate or bicarbonate. Because if I write this as H2CO3, that's carbonic acid. So conjugate, or it's a weak, carbonic acid is a weak acid, so the conjugate base of that weak acid, bicarbonate, or hydrogen carbonate, is also a weak base. Also, it always bothered me that bicarbonate is called bicarbonate, and I only recently looked it up. It has nothing to do with the number of hydrogens. It has entirely to do with how much acid it neutralizes compared to carbonate. So carbonate, CO3 2 minus, is a base. And if I wanted to neutralize HCl, then equilibrium. Write out a basic chemical equation. For every carbonate, I can neutralize 2 HCl's. But if I swap that out with bicarbonate, it neutralizes half as much HCl. And it's called bicarbonate because it takes twice as much. Bicarbonate, you need twice as much carbonate, or twice as much bicarbonate to neutralize the same amount of acid as carbonate. That's why it's bicarbonate. It also goes for bisulfite. Takes twice as much sulfite to neutralize the same amount of acid as sulfite. So it is a very historical name. Bless you. So weak bases, relatively small KBs. Again, a lot of these are amines. So they've got nitrogen, which is acting as the base. And it doesn't really matter how many carbons are attached to that nitrogen. It will still act like a base. Right. So finding the OH minus concentration, we took a little break from ice tables, but I think we're all ready for more. If it's a strong base, how do you think we find the OH minus concentration? Starting molarity. If it's strong base, just like a strong acid, whatever the starting molarity is. There's a little bit of a caveat, a little bit of an asterisk, right? If it's something like calcium hydroxide, then I'm going to get twice as much hydroxide. So just keep an eye out for that. But otherwise, for strong bases, they dissociate completely. So whatever the starting concentration is tells you what the ending concentration is. No real math to be done, or no ice table at least. So barium hydroxide is a strong base. And if you really wanted to do this, I suppose, properly, then you could make some sort of ratio where if I have 1 barium hydroxide, I will get 2 hydroxides. So that's the OH minus concentration. Easy enough. How do I find pH? Yeah, 2 ways to do it really. If you go back to that life of, or the circle of pH, I like to do the negative log of, well, since this is hydroxide, that'll give me POH. Which is 1.69897. And then 14 minus POH will give me pH. So the pH is 12.30. So acidic, basic, or neutral? Basic. Okay. When we're doing this with a weak base, though, methylamine is CH3NH2. I wouldn't expect you to have that memorized. Just like with our acids, we write down the base reacting with water. Or sorry, just like acids, we write down the acid reacting with water, we write down the base reacting with water here also. And then we'll get CH3NH3 plus OH minus. And I've got an initial concentration. These are 0. And then set this all up in the equilibrium expression. Ooh, can I assume X is small? Yes. .4 e to the negative 4 times 0.33 square root. So my OH minus concentration And then 14 minus the negative log. That's not molar, that's pH. Any questions? Practice problems. Do more and more practice problems. Make sure you check your answers. Okay. Yep, cool. This section I find people generally have a hard time with. Trying to figure out if something is going to act, or yeah, for salts and then conjugate acids, conjugate bases, whether or not they are conjugate acids or conjugate bases, or if they're going to be neutral. And the trick generally is, for most things, you add a hydrogen if it's negative. So if it has a negative charge, add a hydrogen. Is that a strong acid or a strong base? Or is that a strong acid? If it's got a positive charge, add a hydroxide to it. Is that going to be a strong base? Because most of this depends on knowing those, well, what are strong acids, strong bases, and then that everything else is a weak acid or weak base. So in this case, we've got bicarbonate or hydrogen carbonate. When that reacts with water, it'll form H2CO3 and hydroxide. So when it's written out like this, it's like, is it going to act as a base or an acid or a base? Well, we have the equation, we end up with hydroxides, it's acting like a base. Most of the time, though, the harder problems are where you're given the salt, which is just an ionic compound. So starting from sodium hydrogen carbonate or sodium bicarbonate, is that going to act like an acid or base? So if I take the sodium and I say, okay, well, Na has a positive charge. If I add hydroxide to that, that's NaOH. Is that a strong base or a weak base? Strong base. And what we mentioned earlier, but probably need a little recap, is if something acts like a strong base or a strong acid, then it's going to be neutral, or its conjugate acid or conjugate base will be neutral. So this is a strong base, a very strong base, dissociates almost completely because there's not a lot of attraction between the sodium and the hydroxide. Which means that if I flip that and I say, if I have just the Na plus in solution, remember, reacts with, or in the base, it loses hydroxide. So I'm asking, will this add hydroxide? Well, the bond between the sodium and the hydroxide was so weak that it loses all of them, so it's not going to be able to pick any up. So sodium, in this case, would be neutral. because it's not going to do that. It won't have an effect on the hydrogens or the hydroxides in the solution. For carbonate, we do the opposite and we say, well, it's HCO3 minus. What if it had another hydrogen? That would make it H2CO3. And then you ask yourself, is that a strong or a weak acid? It's a weak acid. Have we gone over this yet? There's the acronym. I don't really know how to write this out. Hydrobromic, hydroiodic, hydrochloric. Those are all strong acids. This one, the E comes from perchloric. Perchloric, nitric, and sulfuric acids, also strong acids. So carbonate is not, or carbonic acid is not one of those. So this is a weak acid, which means that when I add carbonic acid to a solution, it does not dissociate very much because it has a really strong affinity or bond with that hydrogen. So if I take something like hydrogen carbonate, which doesn't have a hydrogen, it's going to end up taking a bunch of hydrogens. It's a weak acid, or it's the conjugate base of a weak acid. So this is actually a weak base, because this is a weak acid. And so a hydrogen carbonate will make the solution basic. So the trick is, and the thing that you need to practice, is seeing these ions from a salt as conjugate acids or conjugate bases. So any anion we can think of as the conjugate base of an acid. That's why we add a hydrogen to it. Add a hydrogen to it, see which acid it is, or see what acid it's the conjugate base of. So like NO3, nitrate, negative charge, it's an anion. If I add a hydrogen, it becomes HNO3, which is nitric acid, which is a strong acid. As a strong acid, it dissociates almost completely, which means in the reverse, it's not going to pick up any hydrogens. So the conjugate base of a weak acid is itself a weak base. Whereas the conjugate base of a strong acid is going to be pH neutral. It's not going to act as an acid or a base. Won't have any effect on the pH. Again, because strong acids completely dissociate their hydrogens, they won't then pick up any extra hydrogens. Because for something like HCl, well, we can write this as just a one-way arrow because it's going to be all H plus Cl minus. There's really no part of that equilibrium where I have HCl forming again in water. So if I start with Cl minus and water, this reaction doesn't happen where I get HCl and OH minus. So weak acids and weak bases, because there's a more balanced equilibrium, that equilibrium goes both ways. It's like the HCO3 minus equilibrium with H2CO3. I guess I should write it this way. So weaker acid, the stronger the conjugate base. So for example, again, the anion, chloride ion, is pH neutral because HCl is a strong acid. It completely gives up hydrogens. It doesn't want any back. Hydrofluoric acid, though, the F- ion, fluoride, is basic because when you add hydrofluoric acid to a solution, it's a weak acid. It doesn't give up very many of its hydrogens. So if I put fluoride alone in the water, it will suck up hydrogens from its surroundings. It'll take them from water. And so since it takes hydrogens from water, F- will take hydrogens from water. Then I'll get OH minus plus HF. I guess like if you think about it this way too, the equilibrium here, because K is going to be really small, I don't know, something like 10 to the minus 4. Equilibrium favors the reactants. Here, the equilibrium is basically reversed. My equilibrium favors products. Any questions? Okay. There is a nice chart that just sort of summarizes all of this, where I got acid strength on the left, so strong acids at the top, weak in the middle, negligible or essentially neutral at the very, very bottom. And then on the opposite side, base strength increases as you go down. So at the top, things like HCl, H2SO4, or nitric acid, they are neutral because they're strong acids. Including H3O plus is a little bit weird here, but and then for all of these ones in the middle, they're all weak acids. And so their conjugate bases are weak bases. But when we get down to strong bases, things like sulfide and oxide become hydrogen sulfide, but it's, hydrogen sulfide would be H2S. And hydroxide. So these, that one's weird. Oh yeah, as an acid, it's negligible. It's not going to act like an acid at all because it's a strong base. All right, so classify each anion as a weak base or as pH neutral. So what do we need? What do we do? These must be conjugate bases of something. So I want to figure out, these are the conjugate bases of what acid? So I add a hydrogen. Oops. HCHO2. Is that a strong acid? There are 6 strong acids that you need to know. This is not one of them. That means it's a weak acid. So this is a weak acid. What does that make? CHO2 minus. A weak base. So if I add it to solution, will my solution be basic or neutral? Add a weak base to a solution. Does it make the solution basic or neutral? Add a weak base, makes the solution basic. If only slightly. Right, it's a weak base. Maybe we should say that is slightly basic. Formate, formic acid. ClO4 minus. How do we determine if this is a weak base? Add a hydrogen. Figure out if that's a strong acid. ClO4. Is that a strong acid? It is. Perchloric acid. Perchloric acid is a strong acid, which means that perchlorate is going to be pH neutral. Just to give you sort of a math argument for why this is the case. So I don't actually, let's see if I can Google it real quick. The estimated pKa is negative 15.2. So 10 raised to the negative 15.2. No, 10 raised to the positive because it's the negative of the negative. So the Ka of perchloric acid is like 1.58 times 10 to the positive 15, which is really big. So if this is reacting with water, and I will draw an equilibrium arrow because we're talking about equilibrium, but if we're being honest, this isn't really going to have, like this back arrow should be teeny tiny. ClO4 minus. So that Ka is 1.58 times 10 to the positive 15. So that really, really, really favors products. So if I rewrite this as the reverse, right? We can do the 10 to the negative, or I see, raise this to the -1. So we get the inverse. Yeah. It's not the KB. The K for the reverse of this reaction, though, is 6.3 times 10 to the -16. Got to do a little bit more to get actual KB, but the K for this reversed reaction, or the inverse of Ka, right, is 10 to the -16. So how much is chlorate actually going to grab hydrogens to turn back into perchloric acid? Practically none. Practically none at all. So we can say it, quote unquote, acts like a base, or it's like a super, 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 super weak base. There's almost no point in calling it even a weak base because it's so weak that it won't have any effect on the actual pH. When we talk about other weak bases, because we should do it for this, I think there's one. (1.8 times 10 to the -4). So this is formic acid, which CHO2 plus H2O, H3O plus, CHO2 minus. The Ka for this is 1.8 times 10 to the -4. If we give that the same treatment, we want to know what is the inverse. It's 5.6 times 10 to the +5. Which it's a weak acid. It's also going to act like a weak base. So really what we mean when we say like a weak acid or a weak base most commonly means that it has a K that's relatively close to 1. Relatively close. 10 to the -4, 10 to the +5 is a lot closer than 10 to the +15 or 10 to the -16. Because the closer we are to 1, the closer we are to having even amounts of products and reactants. So the strong or the weak acids and the weak bases that we care about have these equilibriums where there's a significant amount of either side of the reaction. If something gets so weak to be 10 to the -16, then we don't even consider it to be a base. And if it's 10 to the +15, this is even an estimated K. You can't even calculate it really because there's not going to be any concentration of the original acid. It dissociates so completely. So some math to back that up in your brain. Everything we apply to acids, we also pretty much apply to bases. Oh, yeah, okay. So here's the relationship between Ka and Kb. So when we calculate if we want to go from the Ka to the Kb, because the issue with these up here that I did is that this is H3O+. So I just took that equation and reversed it. But if I'm adding something that would act as a base, Kb is not the base reacting with H3O+, it's the base reacting with water, which is why down here I have A- plus H2O gives me OH- and HA. The thing that relates these two, actually I want to write this over here. A minus plus H2O. So just rewrote those over each other. So if this is the equation for Ka, this is the equation for Kb. When I add these together, and remember when you add these together, the K's get multiplied. HA cancels out, A minus cancels out, and I'm left with H2O plus H2O. Gives me H3O plus OH minus. In that equation is the autoionization of water, which has its own equilibrium constant, Kw. So if I want to calculate Kw from a Ka and a Kb, it would be Kb, or Ka, times Kb equals Kw. You can also take the negative logs of this, of everything, and get the sort of equivalent pKa plus pKb equals 14. And again, the reason that we have to do this is because the reason we can't just reverse the equation is because my reaction, like that defines Ka, has to be acid reacting with water. If I reverse this, now it's base reacting with H3O plus, not water. Kb is defined as the base reacting with water to produce OH minus. But the commonality between them is Kw. So it can't just convert straight between one or the other. Okay, so this is going to be another ice table, but there are a couple, at least one tricky thing here. So it's asking us to find the pH of a 0.25 molar solution of sodium acetate. Is sodium acetate an acid or a base? It's a base. They gave us Ka. We can't use that Ka for the base. So this is Na plus C2H3O2 minus. So really what we care about is this part. That's going to be our base. This is going to be C2H3O2 minus plus water. Give me OH minus plus H2, HC2, H3O2. So we have to find Kb for this reaction. I mean, we could set up the rest of the ice table, but we're going to need Kb when we actually go to solve it. So Ka times Kb equals Kw. Oh yeah, what's Kw? 1 times 10 to the negative 14. That's always the case. So Kw is 10 to the minus 14, so I can plug in Ka, Kb, Kw, solve for Kb. So Kb equals 5.5 repeating times 10 to the negative 10. And then we go through this and we do the whole ice table thing. Minus x, 2, 5, 0, minus x, 0, 0, x, 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 x. So x squared over 0.250. We can assume this is 0 because 10 to the negative 5. So that times 0.25. And then the square root. 1.1785 times 10 to the negative 5. And that's x. So that will be OH minus. And then we need to find pH. pH is 9.071. Actually, Ka was only 2 sig figs, so it's 9.07. Logs are weird. Yep. Yeah, I didn't write it on there either. I did the negative log, and then I did 14 minus the negative log, and that gave me pH. Slide around 71. All right, there's like 30 slides left. We're talking about diprotic acids.